At the heart of our solar system blazes a star, the Sun, a cosmic furnace that has shaped everything in its domain for billions of years. Orbiting closest to this searing source of energy are four remarkable planets: Mercury, Venus, Earth, and Mars. Though they all fall under the category of terrestrial planets, each tells a wildly different story. From Mercury, a scorched and cratered iron world, to Venus, a planet shrouded in clouds and mystery, to our home Earth, teeming with life, and then to Mars, the dusty red frontier. These are the neighbors we know best, yet still understand so little. In this journey, we will explore the wonders and extremes of the inner planets. What forces shaped them? Why is one a paradise for life, while another is a suffocating oven? And could one of them become our second home? We will dive deep beneath atmospheres, peer into ancient craters, walk through molten plains, and rise into dusty skies. Through missions, measurements, and decades of discovery, science has offered us glimpses of their secrets. But the closer we look, the more questions emerge. This is not just a tour through space. It is a story about heat, history, hope, and humanity's quest to understand its place among the stars. Let us begin. Everyone knows its name. It is the first planet in our solar system, the closest to the Sun, and one of the few celestial bodies visible to the naked eye since ancient times. Mercury has been known to humanity for thousands of years, named after the Roman god of swift travel. Bathed in blinding sunlight, it is never hidden in darkness. And yet, for all its visibility, Mercury is the least explored of the terrestrial worlds. It has remained on the edges of our attention, quiet, distant, and difficult to reach. But this small world holds secrets that few have dared to uncover. It is a planet shaped by fire and impact, metal and silence. It has no moon, almost no atmosphere, and experiences temperatures that swing between extremes unlike anywhere else in the solar system. It is dense, mysterious, and far more dynamic than it first appears. Today, we begin our journey at the very edge of the solar furnace, on a planet that has quietly endured for billions of years. Welcome to Mercury. At first glance, Mercury might seem like a simple place, a small, rocky ball orbiting close to the Sun. But simplicity is often an illusion in astronomy. Mercury is, in fact, one of the most intriguing planets in our solar system. It is the smallest of the 8 planets, measuring just under 5,000 kilometers in diameter. That is roughly 1/3 the width of Earth. Its size alone might lead one to overlook it, but what Mercury lacks in scale, it makes up for in density, structure, and mystery. Despite being so small, Mercury is incredibly dense. Its average density is approximately 5.4 grams per cubic centimeter, second only to Earth. This high density suggests a large metallic core, making up about 85% of the planet's radius. In fact, Mercury is more metal than rock. Around 70% of its mass is metallic, with the rest composed of silicate material. If it were the same size as Earth, it would have nearly the same surface gravity. But because of its tiny size, the actual gravity is much weaker, only about 38% of Earth's pull. To put Mercury's size into perspective, let us compare it with two familiar moons, Ganymede and Titan. Ganymede, the largest moon of Jupiter, and Titan, Saturn's largest moon, are both larger in diameter than Mercury. But here is the astonishing part. Despite being bigger, they are far less massive. Ganymede and Titan are composed mostly of ice and rock, whereas Mercury is a heavy, iron-rich world. It may be smaller, but Mercury outweighs them by far. It is not just a leftover rock. It is a dense, ironclad survivor of the early solar system, forged in heat and shaped by collisions. The surface of Mercury is a frozen record of ancient violence. At first glance, it resembles our moon, gray, battered, and marked by countless craters. But look closer, and subtle differences emerge. Mercury's surface tells a story of intense geological activity long in the past. Vast plains of solidified lava stretch across regions once shaped by fire. These smooth plains are thought to have formed from ancient volcanic eruptions, pouring over the landscape and slowly cooling into a hardened crust. Yet, unlike Earth or Venus, Mercury's surface has remained largely unchanged for billions of years. One of the most dramatic features on Mercury is the Caloris Basin, a massive impact crater spanning 1,550 kilometers in diameter. It was formed by a colossal asteroid strike during the early solar system. The impact was so powerful that it fractured the planet's crust and triggered waves of volcanic eruptions. Surrounding the basin is a circular mountain range towering more than 2 kilometers high, a scar frozen in time. But what truly stuns scientists is what lies on the opposite side of the planet, the mysterious, weird terrain where the shockwaves from the Caloris impact converged and warped the crust into chaotic hills and ridges. This strange and jumbled landscape, with no clear pattern or symmetry, defies easy explanation. It looks as if the planet's skin was crumpled and torn. Scientists believe that when the Caloris impact occurred, seismic waves traveled through Mercury's interior and focused their energy directly on the antipodal point, creating the weird terrain. These waves fractured and distorted the surface, producing a region unlike any other in the solar system. Mercury may appear static today, but its surface is a battlefield of cosmic violence, one that still echoes the energy of a young and turbulent solar system. Mercury orbits the Sun faster than any other planet, completing a full circuit in just 88 Earth days. But while it races around the Sun, it spins incredibly slowly on its own axis. One full rotation takes 59 Earth days. This unusual combination creates one of the strangest phenomena in the solar system. Mercury's solar day, the time between two sunrises, is nearly 176 Earth days long. That means one day on Mercury, from sunrise to the next sunrise, lasts the equivalent of 2 Mercury years. It is a world where time itself feels stretched and twisted. Even stranger is what you would see if you stood on Mercury's surface during sunrise. As the sun climbs over the horizon, it begins to rise, and then slows. And then something extraordinary happens. Just before Mercury reaches its closest point to the sun, called perihelion, the sun appears to pause in the sky, then reverse direction and move backward for several Earth days. After this brief rewind, it resumes its normal course and continues to set. This optical illusion is not caused by the sun moving, of course, but by Mercury's highly elliptical orbit and its unique 3-2 spin-orbit resonance. This resonance means that for every 2 orbits Mercury makes around the Sun, it rotates exactly 3 times on its axis. It is a cosmic dance locked in perfect rhythm. Because of this, certain longitudes on Mercury experience sunrises only once every 2 Mercury years. If you were standing on one of these spots, you could see the same sunrise during each close approach to Earth, which once led astronomers to mistakenly believe Mercury was tidally locked. It was only with radar observations in the mid-20th century that the true rotational behavior of Mercury was finally revealed. What seems simple from afar is, in fact, a masterpiece of celestial mechanics. Reaching Mercury is one of the most challenging feats in planetary exploration. The Sun's immense gravity accelerates any spacecraft flying inward, making it far more difficult to slow down than to speed up. Traditional propulsion would require massive amounts of fuel, more than a spacecraft could realistically carry. For decades, Mercury remained largely untouched after the brief flybys of Mariner 10 in the 1970s. But then came Messenger, a mission that changed everything. Instead of brute force, it relied on gravity, using flybys of Earth, Venus, and Mercury itself to gradually decelerate over a journey of 6.5 years. Messenger, short for Mercury surface, space environment, geochemistry, and ranging, launched in the year 2004. It traveled nearly 8 billion kilometers before finally entering orbit around Mercury in 2011. Its path included 1 flyby of Earth, 2 of Venus, and 3 of Mercury, each one carefully calculated to bleed off velocity. It even used its solar panels like sails to catch solar radiation, applying a gentle counterforce to slow its descent. The result was an elegant ballet of orbital mechanics, allowing the spacecraft to settle into an elliptical orbit ranging from 200 to 15,000 kilometers above the surface. Once in orbit, Messenger delivered far beyond expectations. Originally planned for a single year, it operated for over 4, capturing more than 200,000 high-resolution images and mapping 100% of Mercury's surface. Among its many discoveries were vast volcanic plains, hollowed-out surface depressions unlike any seen elsewhere, and strong evidence of water ice hidden in permanently shadowed craters near the poles. It also revealed that Mercury has a dynamic magnetic field and an oversized iron core that extends far closer to the surface than previously believed. Messenger showed us a planet we thought we knew, and proved how wrong we were. Mercury, though silent today, was once a world of fire. The surface bears the unmistakable marks of ancient volcanic activity. Vast plains were flooded by lava, smoothing out terrain and filling massive craters. In places like the Raditladi and Rachmaninoff basins, you can still see where molten rock once bubbled up from below, forming smooth floors and circular ridges. Beyond these lava fields, towering cliffs known as scarps stretch for hundreds of kilometers. These steep, cliff-like features are believed to be the result of Mercury's slow contraction as its core cooled, signs that the planet is literally shrinking over time. But Mercury's secrets do not stop at its surface. High above, an ultra-thin exosphere surrounds the planet, composed of atoms blasted off the crust by solar radiation and micrometeoroid impacts. Unlike a true atmosphere, the exosphere is so sparse that particles rarely collide. Yet it is dynamic and ever-changing. When the solar wind hits Mercury, it strips atoms from the exosphere and drags them away into space, forming a long glowing tail, much like that of a comet. Sodium atoms in particular give this tail a faint yellow hue. From a distance, Mercury briefly becomes not just a planet, but a burning ember with a shimmering trail. Venus is a planet of contradictions. From afar, it appears serene, wrapped in soft golden clouds and shining brighter than any planet in the night sky. It has long been a symbol of beauty, bearing the name of the Roman goddess of love. But behind that glowing exterior lies a world more hostile than any other in the solar system. A place where the air crushes like the depths of an ocean, where acid rains from the skies, and where the surface temperature can melt lead. Venus is not a gentle goddess. It is a planet forged in fury. In many ways, Venus is Earth's twin. It is similar in size, mass, and composition, and yet their destinies could not have diverged more sharply. How did one planet become a cradle for life, while the other descended into a choking greenhouse inferno? What happened beneath those thick clouds? In this chapter, we will peel back the layers of Venus, its slow, backward spin, its crushing atmosphere, and its volcanic plains, to reveal a world that defies our expectations. Welcome to Venus, the brilliant mirror of Earth, and perhaps its most haunting warning. Venus is the second planet from the Sun, orbiting at a distance of approximately 108 million kilometers. It follows the most circular orbit of any planet in the solar system, with a nearly perfect path that deviates only slightly from a true circle. Because of its proximity to Earth and its reflective cloud cover, Venus is the brightest natural object in our night sky after the Moon. Often visible near sunrise or sunset, it has been called both the morning star and the evening star for centuries, a shining beacon that once guided ancient travelers across land and sea. But Venus is also a planet full of surprises, beginning with the way it spins. Unlike most planets, which rotate in the same direction they orbit, Venus spins backwards. This retrograde rotation means that if you stood on its surface, the sun would appear to rise in the west and set in the east. Even more curious is how slowly it turns. Venus takes 243 Earth days to complete a single rotation, making its day longer than its year. A year on Venus, the time it takes to orbit the Sun, is only 224 Earth days. It is one of the slowest spinning objects in the solar system. Due to this strange combination of slow rotation and backward spin, Venus has an unusual day-night cycle. A solar day, the time from one sunrise to the next, is about 117 Earth days. In other words, if you stood on the surface, you would see only 2 sunrises during each Venusian year. This peculiar rhythm gives Venus its own sense of time, one that challenges our Earth-based intuitions. It also contributes to the extreme climate, as the planet's slow spin offers ample time for heat to accumulate beneath its thick clouds. Time, light, and motion. On Venus, none behave the way you would expect. As we descend beneath the golden clouds of Venus, we enter one of the most extreme environments in the entire solar system. The pressure here is staggering. At the surface, the atmospheric pressure is over 90 times greater than what we experience on Earth. That is equivalent to being submerged 1 kilometer beneath the ocean. Any unprotected spacecraft or person would be crushed instantly. The weight of this atmosphere presses down with relentless force, a reminder that Venus is not just hot, but heavy. It is not a world that gently welcomes visitors. It is a planet that resists intrusion. This oppressive pressure comes from a massive atmosphere made up almost entirely of carbon dioxide. About 96% of Venus's atmosphere is composed of this greenhouse gas, with only small traces of nitrogen and other elements. Floating above the surface are thick clouds of sulfuric acid, dense and reflective. They scatter sunlight, giving Venus its brilliant glow in our sky. But while these clouds shine on the outside, they act like a thermal blanket on the inside, trapping heat and preventing it from escaping back into space. The result is a world in thermal lockdown, where energy goes in but very little comes out. The greenhouse effect on Venus is not just strong, it is the strongest in the solar system. The average surface temperature is around 460 degrees Celsius, hot enough to melt lead. And this heat is remarkably stable. Unlike Mercury, which sees wild temperature swings between night and day, Venus maintains a near constant temperature across its entire surface. Whether at the poles or the equator, in daylight or darkness, it remains scorching. The dense carbon dioxide traps infrared radiation with incredible efficiency, turning the planet into a slow cooking furnace that never cools. Even the winds on Venus cannot offer relief. Near the surface, the air moves slowly, just a few kilometers per hour. But because the atmosphere is so thick, even a gentle breeze has the force of a strong gust on Earth. Higher in the atmosphere, winds race at over 300 kilometers per hour, circling the planet in just a few Earth days. These upper winds create powerful jet streams that churn the clouds and distribute heat globally. Yet despite this constant motion, the heat remains locked in, unable to escape the dense carbon dioxide prison that blankets the world. What happened here? How did a planet so similar in size and mass to Earth become so catastrophically different? Many scientists believe that Venus once had a more temperate past, perhaps even oceans of liquid water. But as the sun grew brighter and the climate warmed, water began to evaporate. Water vapor, itself a greenhouse gas, accelerated the warming. Eventually, carbon dioxide was released from the rocks in vast quantities, and Venus crossed a point of no return, a runaway greenhouse effect. Today, it stands as a stark warning. The same physical laws that shaped Earth also apply here, with very different results. Long before modern space agencies turned their gaze toward Venus, it was the Soviet Union that first dared to reach its surface. In an era dominated by Cold War competition, the Soviet Venera program became one of the boldest and most underrated achievements in the history of planetary exploration. Starting in the early 1960s, a series of increasingly ambitious spacecraft were launched toward Venus. Many failed. Some burned up in the atmosphere. Others were crushed before they could send back data. But through trial and perseverance, Venera missions eventually achieved what was once thought impossible. In the year 1975, Venera 9 became the first spacecraft in human history to send back images from the surface of another planet. What it revealed was stunning. A barren, rocky plain under a thick yellow sky, lit dimly through layers of choking clouds. The rocks were flat and fractured, like ancient lava flows frozen in time. Venera 10 followed soon after, delivering similar photographs from a different landing site. These haunting images remain the only photographs ever taken from the surface of Venus. They are not computer renderings or artist impressions. They are real windows into another world. The later missions, such as Venera 13 and Venera 14, pushed even further. They carried sophisticated instruments to study soil chemistry, surface composition, atmospheric layers, and pressure. Venera 13 lasted over 2 hours on the surface, transmitting color images, recording sounds, and analyzing samples before succumbing to the crushing heat. These missions confirmed that the Venusian rocks were volcanic in origin, and that the thick atmosphere was composed almost entirely of carbon dioxide. Despite the incredible pressure, corrosive clouds, and intense temperatures, these Soviet probes stood their ground, if only briefly. No spacecraft has landed on Venus since the era of the Venera missions. In many ways, their success remains unmatched. Even today, landing a functioning probe on the surface of Venus is considered a near impossible challenge. Yet decades ago, engineers managed it with slide rules, analog computers, and raw determination. The Venera program did not just expand our understanding of Venus. It reminded us of what human ingenuity can achieve, even under the most daunting conditions. Through the static and heat, through the silence of another world, came the first, and still only, clear images from the surface of Earth's mysterious twin. Because of Venus's thick cloud cover, traditional optical imaging is impossible. No camera can peer through the sulfuric acid haze to see the surface below. To overcome this, scientists turned to radar. In the early 1990s, NASA's Magellan spacecraft used synthetic aperture radar to pierce the clouds and map over 98% of Venus's surface with astonishing detail. What it revealed was a world dominated by volcanic activity. Vast lava plains stretch across the planet, covering millions of square kilometers, with smooth textures and winding channels carved by molten rock. Unlike Earth, where plate tectonics break and reshape continents over time, Venus appears to have no moving plates. Instead, its surface tells a different story, one of catastrophic resurfacing. The Magellan data showed that Venus lacks the expected accumulation of old impact craters. Most of its surface appears relatively young, geologically speaking, only a few 100 million years old. This led to a dramatic hypothesis. At some point in its past, Venus underwent a global resurfacing event. Massive volcanic eruptions may have poured out enough lava to bury nearly all older terrain, resetting the surface in a geological flash. Radar mapping also revealed features known as coronae, vast circular structures formed by upwelling magma pushing against the crust. These, along with pancake domes, lava flows, and rift valleys, suggest that Venus may still be geologically active today. In fact, recent studies based on subtle changes in surface brightness hint that volcanic activity might still be ongoing. While we have no direct observations yet, the scars on Venus's surface suggest that the planet is far from dead. Beneath its crushing atmosphere and ancient lava plains, a restless heart may still beat. At the poles of Venus, something strange is always spinning. Using infrared imaging, scientists have discovered massive, persistent vortex structures at both poles, gigantic whirlpools of cloud and gas, swirling endlessly in double-eyed spirals. These polar vortices are vast, dynamic systems that shift shape over days and weeks, resembling the eye of a hurricane, but far more complex. Unlike anything seen on Earth, they form in an atmosphere thick with carbon dioxide and sulfuric acid, stirred by extreme temperature gradients and violent winds. Venus is not still. It is in constant, chaotic motion, especially near its mysterious poles. Within the dense Venusian clouds, sulfuric acid rains down in corrosive droplets. These rains do not reach the surface. They evaporate in the searing heat long before making contact with the ground. Above, in the upper cloud decks, hurricane-force winds whip around the planet at more than 300 kilometers per hour, circling Venus in just a few Earth days. This phenomenon, known as superrotation, means that while the surface crawls beneath crushing pressure, the skies above are locked in a never-ending storm. It is a world of chemical fury, where acid rains fall sideways and clouds race faster than the planet itself spins. And yet, amid this chaos, a curious signal emerged. In the year 2020, scientists reported traces of phosphine gas in the upper atmosphere of Venus. On Earth, Phosphine is produced by microbial life in oxygen-free environments or through industrial processes. Its presence on Venus raised an extraordinary question. Could something be alive in those acidic clouds? The detection is still debated, and alternative explanations are being explored. But it sparked renewed interest in Venus as a possible host for exotic life. Life not on the surface, but floating in the clouds of a planet once thought entirely dead. Among the 8 planets in our solar system, Earth holds a special distinction, not just for its ability to harbor life, but for the delicate balance of its physical properties. With a diameter of about 12,700 kilometers, Earth is neither the largest nor the smallest, but it is perfectly suited for its role. Its mass and gravity create the ideal conditions for a stable atmosphere, a protective magnetic field, and the retention of liquid water. When viewed from space, Earth appears as a near-perfect sphere, but it is actually an oblate spheroid, slightly flattened at the poles and bulging at the equator due to its rotation. This rotation is more than just a cosmic spin. It shapes the very nature of our planet. The tilt of Earth's axis, angled at approximately 23.5 degrees, gives us seasons. It causes the sun to rise and set at different points throughout the year and allows different parts of the planet to experience cycles of warmth and cold. Without this axial tilt, Earth would have no seasonal variety, no spring blossoms, no autumn leaves. It is a subtle angle, but it is responsible for the rhythms of agriculture, ecosystems, and life itself. This quiet inclination carries immense consequences. Beneath its surface, Earth generates an invisible shield. The molten iron core spins, creating a powerful magnetic field that extends far into space. This magnetosphere deflects solar wind and cosmic radiation, protecting our atmosphere from being stripped away. It is the reason compasses point north, but it is also a guardian of habitability. Without this magnetic shield, Earth's surface would be bombarded by charged particles from the sun, damaging satellites, disrupting communication, and possibly eroding the very conditions that sustain life. Earth's field is unseen, but it may be one of its most essential traits. When we speak of a day on Earth, we usually mean the solar day, the time it takes for the sun to return to the same point in the sky from one noon to the next. This is the familiar 24-hour cycle that governs our clocks, calendars, and daily routines. But there is another kind of day, the sidereal day. This is the time it takes for Earth to complete one full rotation relative to the distant stars, not the sun. It is slightly shorter, lasting about 23 hours and 56 minutes. The difference arises because Earth is also orbiting the sun, so it must rotate a bit more than once to bring the sun back to the same position in the sky. This subtle distinction between solar and sidereal days leads to a beautiful phenomenon called the analemma. If you photographed the sun from the same spot on Earth at the same clock time every day for a year, the sun's position would trace a looping figure-8 pattern in the sky. This shape results from the combination of Earth's axial tilt and its elliptical orbit around the sun. The analemma shows how the sun appears to drift north and south over the seasons, and also slightly ahead or behind time, depending on the date. It is a visual fingerprint of Earth's dynamic motion through space. The analemma is more than a curious shape. It tells us that time itself is not perfectly regular when measured by the sun. Sundials drift from mechanical clocks, sometimes by more than 15 minutes. That is why we have the equation of time, a correction that accounts for this discrepancy. It reminds us that our notion of a day is a compromise, shaped by both celestial mechanics and human convenience. Earth's spin is not just a constant turning. It is an intricate dance with the sun and stars, creating the cycles that define not only how we live, but how we understand time itself. Earth's atmosphere is a delicate veil, thin in scale, yet vast in influence. Composed primarily of nitrogen and oxygen, with traces of argon, carbon dioxide, and other gases, it surrounds our planet like an invisible ocean. It provides the air we breathe, the pressure that holds water in liquid form, and the protection we need from space-borne dangers. But this mixture is not static. It is dynamic, layered, and complex. Each component plays a role, from oxygen fueling life and fire, to carbon dioxide regulating temperature, to water vapor shaping clouds and storms. It is a system in constant motion, yet in remarkable balance. Among the many layers of the atmosphere, the ozone layer stands out as one of the most critical. Located in the stratosphere, this thin band of ozone molecules absorbs the majority of the sun's harmful ultraviolet radiation. Without it, life on land would be impossible. Plants, animals, and human skin would suffer severe damage from unfiltered UV rays. The ozone layer acts as Earth's sunscreen, quietly shielding us from an invisible threat. Its depletion in the 20th century triggered a global scientific and political response, and its recovery today is a rare story of environmental success and planetary cooperation. The atmosphere is also the stage for the water cycle, Earth's continuous system of evaporation, condensation, and precipitation. Oceans, lakes, rivers, clouds, and rain are all part of this great planetary loop. Heat from the sun drives water into vapor. Air currents carry it high into the sky, and as it cools, it forms clouds and returns as rain or snow. This cycle shapes weather, nourishes ecosystems, and carves the surface of the Earth. It also acts as a heat regulator, absorbing energy during evaporation and releasing it during condensation. The water cycle is not only about movement, it is a vital mechanism of temperature control and life support. And then there is the greenhouse effect, the process by which gases like carbon dioxide, methane, and water vapor trap infrared radiation and warm the planet. On Earth, this effect is moderate and balanced. It keeps our planet at a livable average temperature, far warmer than it would be without an atmosphere. Unlike Venus, where the greenhouse effect runs unchecked, Earth's atmosphere maintains equilibrium through feedback loops, cloud cover, and the carbon cycle. But this balance is fragile. Even small changes in greenhouse gas concentrations can tip the scales, reminding us that the atmosphere is not just a blanket. It is a thermostat we must learn to respect. Beneath Earth's surface lies a world of immense heat and pressure, a layered architecture that shapes everything we see above. The outermost shell, the crust, is relatively thin and fragmented, floating atop a semi-fluid mantle. Beneath that mantle is the core, composed of a solid inner sphere and a molten outer layer made mostly of iron and nickel. These inner workings are far from static. Heat from the core drives convection currents in the mantle, pushing and pulling the surface above. This hidden engine is the source of tectonic motion, volcanic activity, and the restless reshaping of continents. Unlike any other planet we know, Earth is alive with tectonic motion. Its crust is divided into massive plates that drift atop the mantle's currents. These tectonic plates collide, pull apart, and slide past one another, forming mountains, ocean trenches, and earthquake zones. The shifting of these plates is not destruction, it is renewal. Continents have merged and broken apart over billions of years, reshaping climates and ecosystems. Volcanoes born from subduction zones release gases that replenish the atmosphere. Earth's surface is not fixed. It breathes, shifts, and evolves through the slow dance of plate tectonics. The churning of molten metals deep within Earth's outer core generates a vast magnetic field, extending tens of thousands of kilometers into space. This magnetosphere shields the planet from solar wind and cosmic radiation, deflecting harmful particles that would otherwise strip away our atmosphere. Occasionally, some of these charged particles spiral down along magnetic field lines toward the poles, colliding with atmospheric gases to produce auroras, curtains of green and red light dancing in the polar skies. The aurora is not just a spectacle, it is the visible whisper of Earth's magnetic protection. High above, the moon silently tugs at Earth's oceans. Its gravity stretches the seas into bulging tides, creating the rhythmic rise and fall we see along every coast. This tidal effect is more than a daily occurrence. It shapes ecosystems, migratory patterns, and even the rotation of our planet. Over time, the tidal friction caused by the moon's pull has gradually slowed Earth's spin and nudged the moon farther away. Without this influence, Earth's rotation would be faster, and days would be shorter. The moon is not just a passive satellite, it is a sculptor of planetary rhythm. Beyond tides, the moon performs a subtler, stabilizing role. Earth's axis is tilted, and that tilt gives us our seasons. But the gravitational pull of the moon helps keep that tilt steady. Without the moon, Earth's axial tilt could wobble chaotically over time, triggering extreme climate swings. The moon acts as a cosmic gyroscope, guarding the delicate balance that allows for long-term climate stability. This quiet influence may have been essential for the development of complex life, giving Earth the steady seasons and temperate environments that evolution thrives on. Some scientists believe the moon's formation was not just a coincidence, but a critical chapter in Earth's story. Formed from a massive collision in the planet's youth, the moon may have helped strip away a thick early atmosphere, cooled the young Earth's surface, and set the stage for plate tectonics to begin. Its tidal forces stirred the primordial oceans, possibly aiding in the chemical mixing that led to the first living molecules. From geology to biology, from tides to timekeeping, the moon's presence has shaped Earth's path in quiet but profound ways. It is not merely a satellite, it is a silent architect of our planet's evolution. Mars orbits the Sun at a greater distance than Earth, taking nearly twice as long to complete one full revolution. A Martian year lasts about 687 Earth days, but its day, called a sol, is surprisingly close to ours, lasting just over 24.5 hours. The planet's axial tilt is also similar to Earth's, at about 25 degrees, which means Mars experiences seasons. These seasons are longer and more extreme, shaped by its elliptical orbit and thinner atmosphere. Although its surface appears barren, the rhythm of time on Mars feels strangely familiar. Days, years, and seasons shaped by the same solar forces that govern Earth. Mars is home to the largest volcano in the solar system, Olympus Mons. Rising more than 20 kilometers above the Martian plains, this towering shield volcano would dwarf Mount Everest several times over. It is so wide that its base could cover the entire state of New Mexico. Just as impressive is Valles Marineris, a massive canyon system that stretches over 4,000 kilometers, longer than the continental United States. It plunges up to 7 kilometers deep in places, carved by tectonic tension and possible ancient water flow. These colossal features hint at a planet that was once geologically alive, its crust shaped by fire and fracture on a scale Earth can barely imagine. One of the most iconic traits of Mars is its rust-colored surface, giving it the nickname the Red Planet. This hue comes from iron-rich dust and rocks coated in iron oxide, essentially planetary rust. Over billions of years, this dust has spread across the surface, covering valleys, hills, and craters in a blanket of reddish-orange. But beneath the surface, Mars is not all red. In some regions, the soil turns gray, black, or even blue in shadow. The thin atmosphere allows wind to whip these colors into swirling dust storms that can engulf the entire planet. Mars wears its age in iron and wind, a rusting relic in the cold sunlight. Though it may seem frozen in time, Mars is far from motionless. Landslides ripple down crater walls, changing the landscape in ways we can watch from orbit. In the southern polar regions, something truly alien happens. As spring sunlight penetrates layers of carbon dioxide ice, the gas trapped beneath explosively escapes through cracks, carving strange radial patterns into the surface. These formations, called spiders, are unlike anything on Earth. They show that even without liquid water or tectonic movement, Mars remains an active world, one driven by pressure, sunlight, and sublimating ice. Recent missions have captured images of impact craters, revealing bright patches of subsurface ice. When meteors strike, they blast away the surface dust, exposing what lies just beneath, a frozen layer rich in water. Sometimes, these collisions cause that ice to rapidly vaporize or briefly melt, darkening the surface and creating temporary stains. Such events offer clues to the planet's buried reservoirs of water and suggest that Mars is not entirely locked in geological silence. Even in its thin atmosphere and bitter cold, energy still moves beneath the surface, hinting at reservoirs of ice, chemistry, and perhaps, long ago, life. Mars is a world shaped by wind. With an atmosphere less than 1% the density of Earth's, you might expect little weather at all. But what Mars lacks in pressure, it makes up for in persistence. Winds sweep across its barren plains, lifting fine, iron-rich dust into the air. Sometimes, this dust grows into swirling towers called dust devils, tall, dancing columns that leave dark trails etched across the ground. And in rare events, storms do not just sweep regions, they engulf the entire planet. These global dust storms can last for weeks, turning day into twilight and hiding the surface beneath a reddish haze. They are beautiful, but they are also deadly. The Martian climate is one of extremes. Temperatures near the equator can briefly rise above freezing during the day, but plunge to bone-shattering cold at night. At the poles, carbon dioxide freezes straight out of the atmosphere each winter, creating polar caps that grow and shrink with the seasons. Thin air and lack of moisture mean that heat escapes quickly, and storms can rage without rain. There are no oceans to soften the seasons, no dense atmosphere to trap heat. Mars is a planet stripped down to elemental forces: wind, dust, sunlight, and silence. Surviving here would require not just technology, but a deep understanding of how alien and unstable this environment truly is. Billions of years ago, Mars may have had a thick atmosphere, running water, and even oceans. But something changed. Without a protective magnetic field, solar wind from the sun gradually stripped away its atmosphere, molecule by molecule. Over time, what was once warm and wet became cold and dry. To understand this transformation, NASA launched the MAVEN spacecraft, the Mars Atmosphere and Volatile Evolution mission. MAVEN orbits the planet today, studying how solar particles interact with the upper atmosphere, measuring the rate at which gases still escape into space. Its findings reveal that Mars is still bleeding air into the void, and that its past habitability was undone not by violence, but by slow and silent loss. Unlike Earth, Mars does not have a global magnetic field to shield it from the sun's radiation. Some regions contain localized, fossilized magnetic fields locked into ancient crustal rock, but these are fragmented and weak. This lack of magnetic protection is why solar wind could strip the atmosphere so efficiently. It also means Mars is exposed to intense cosmic radiation, making its surface far more dangerous for future explorers. Understanding this vulnerability helps scientists evaluate where and how humans might one day survive on Mars. The story of its vanished magnetosphere is not just about physics. It is about why a once Earth-like planet lost its potential for life. Mars has two tiny moons, Phobos and Deimos. Unlike our moon, they are irregularly shaped, more like captured asteroids than true satellites. Phobos, the larger of the two, orbits Mars at a dangerously close distance, completing a full revolution in under 8 hours. Tidal forces are pulling it inward, causing surface fractures and triggering fears of a future collapse. Within a few tens of millions of years, Phobos may break apart entirely, forming a temporary ring around Mars. Meanwhile, Deimos drifts slowly outward. These moons occasionally pass in front of the Sun, casting fleeting eclipses across the Martian sky. Not grand like on Earth, but eerie, jagged shadows of dying moons on a planet that has lost so much. Four planets, orbiting close to the Sun, born from the same swirling disk of gas and dust. And yet, each one tells a different story. Mercury, with its scorched silent surface and oversized iron heart. Venus, veiled in clouds of poison, where pressure crushes and heat melts. Earth, vibrant and balanced, the only world we know to host life. And Mars, a rusted time capsule, hinting at a wetter, warmer past. Their temperatures span hundreds of degrees, their atmospheres range from absent to suffocating, and their gravities shape how matter moves and how futures unfold. Together, they form a gallery of planetary identity, an atlas of what worlds can become. Among them, only Earth sits in the narrow band of possibility, a rare harmony of pressure, temperature, and chemistry. Mercury is too small, too bare, baked and battered beyond habitability. Venus is a warning, the runaway greenhouse effect in full bloom, a planet undone by its own skies. Mars is colder and drier now, but not always. It holds echoes of rivers, lakes, and something more. In its ancient soils may lie the memory of microbial life. These four worlds form a spectrum, from the utterly hostile to the almost promising. And in that range lies insight, not only into our origins, but into our future. What makes a planet livable? What makes it stay that way? The story of these worlds is far from over. In the vacuum between planets, machines continue their silent journeys. BP Colombo is en route to Mercury, aiming to map its surface and magnetic mysteries in greater detail than ever before. Da Vinci Plus will plunge through the thick clouds of Venus, sampling its hellish atmosphere and seeking clues about its lost oceans. And on Mars, the Perseverance rover prepares samples for a return to Earth, samples that may hold signs of past life. These missions are not just scientific, they are expressions of curiosity, of the human need to understand. With every launch, we add another thread to the tapestry of planetary knowledge. In these four inner planets, we see our past and our potential. We see what happens when a planet clings too tightly to its heat or loses its grip on its air. We see volcanic worlds without water, icy worlds without life, and our own world with both. They teach us humility, how narrow the path to habitability truly is, and they teach us urgency, how easily that path can disappear. Venus may show us what happens when climate spirals beyond control. Mars may show us the limits of planetary protection. Earth stands between them, a fragile balance we must learn to maintain. The others do not just orbit, they warn. We began this journey near the Sun, in a realm of heat, radiation, and extremes. But even here, where the light is harshest and survival seems impossible, we find beauty, complexity, and meaning. The closer we look at these planets, the more we see reflections of ourselves, the fragility of balance, the resilience of matter, the mystery of time. Our solar system is not just a collection of rocks, it is a laboratory of possibility. And the inner worlds, though small and silent, still hold answers we have barely begun to ask. There is still light left to explore, and still so many shadows to understand. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.